All right, so let's go through this homework assignment here. So the first one is a V equals IR problem. So you've got, let's see here. If you just do V equals IR and you get 7 amps times 4 ohms, then you get, I don't know what that is, 4 ohms. We get 28 volts. And then so what we want to do is order the resistors by voltage across them. So you do that for each of these 28 volts, 6 volts, 16 volts, and 36 volts. And you just drag them in. Okay. Cook a chicken. I don't know what that is. It's in do not disturb mode. I don't know why. Okay, next one. When a wire has a large diameter length that is connected across terminals of an automobile battery, the current is 40 amps. If we cut the wire to half its original length and connect one piece that has length L/2 across the terminals of the same battery, the current will be, so for this one, we have the resistance equals rho L/A. And so we've got a wire with a large diameter and a length L. So if we cut the wire to half and connect, so then we just basically cut it in half. What's going to happen to the current? So the R new is going to be rho L/2A, and so that means L is equal to let's see, 2A R new over rho. Is that what I want to do? If I plug that back in here, I get that. Oh no, so let me go the other way. So this one, L is equal to AR over rho. So if I plug that in here, R new is rho times AR over 2A rho. So rho cancels out, A cancels out. So R new is equal to half of R. And so if V equals IR, and then we have the same voltage, so V is equal to I new times R new, and this is equal to I new times half R, half initial R. So that means the current is going to have to be, it's going to end up being twice. So we'd end up with 80 amps. Delete. Okay, certain wires length L, resistance R is stretched uniformly length 2L. What is it after it's stretched? So this is a little bit tricky problem. We've got a wire, and then we stretch it uniformly to 2L. And what's going to happen is it's going to get a little bit thinner when we stretch it. So this is a little bit of a tricky problem because basically you've got rho is equal to, or resistor is rho L over A. And now what we care about is that the mass per volume is defined as the density of the material, and since we're stretching it, the mass per volume isn't going to change. And this rho is the density rho. It's different from the resistivity rho. So mass per volume equals this density. So the same mass and the volume is going to be pi r squared times the length, and that's going to be the relationship to the density. So if we make the length 2L, then L new is equal to 2 times the original L. Then we'll do the same thing we did in the earlier problem. You plug in what your new L is, and that's going to get you your relationship to your area, which is pi r squared. And so you keep this constant, plug that back in, and then solve for what your R is going to be. If your new L, you get L over 2 here. L new is 2L, and then your area is going to, cross-sectional area is going to go down because your density is going to be the same. And so what ends up happening, you have the same mass, and then you have pi, and then R new squared times L new, and L new is 2L, so you put 2L in here, come on, there you go, 2L, and then solve for what your new radius is. plug that in for your cross-sectional area, and you get what your new resistance is. Okay, so delete that. Number 4, 2 copper wires are the same length, but one is twice the diameter of the other. Compared to the one that has a smaller diameter, the one that has a larger diameter has a resistance that is what? So at the same length, one is twice the diameter. So the resistivity of one is equal to rho L over, and this is going to be pi r squared, and then R2 is going to be rho, because they're both copper, same length, over pi R2 squared, okay? And the diameter is twice that. So this is going to be actually 2r squared. Sorry, 2r. Let's see. Yeah, it's twice the length, so twice the radius. And if it's twice the diameter, twice the radius, it's the same. Okay, compared to the one of those larger diameter has the, okay, so then what you do is you divide the two of them, and you get R1 over R2 is equal to, the rho's cancels, the pi's cancels, the l's cancel. You end up with 4r squared over r squared. Cancel that out, so one of them's 4 times bigger than the other. Okay, delete that. Next one. The resistance of copper wire depends on the material's resistivity and the length of the cross-sectional wire. What happens if the resistance of the wire is multiplied by 5? Okay, so I'm not going to do this one because it's a little bit long, and it's just R equals rho L over A. And so you're just, let's do resistor is rho L over A. What happens if you multiply the length by 5? Then your resistance is going to be increased by 5. So do that problem. 6. So we want to order these circuits by their power usage from lowest to highest. And so the way you do this, so all the batteries are the same voltage, all the lights are the same resistance. So we've just got, we're going to try to do our P equals IV thing, and order them by that. All batteries are the same voltage, all light bulbs have the same resistance. So in this, let's say we have R and R here. Well, we know that the net thing is half of R when you have 2 like resistors in parallel. So the power is I squared times a half R, or V over R. So you could do V over, the resistance here would be half R, so it would be 2V over R. For this one, you'd have V over R, V over R. The power here is V over R. And then same thing, sorry, I just drew on that. Same thing here, you've got 3V over R here because you've got 3 resistors in parallel. So they add up, since they're like resistors, a third of the power. And then over here you have V equals IR equals IR equals IR, V. So they all have the same voltage drop. So you have, add them all up, bing, 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 and then do the same thing here. So there's 2 of them, V equals IR, V equals IR. Current's the constant, R is the same, so each voltage drop is the same. And then you just sort them by that. Okay, delete. 7. Common electrical wall receptacle voltage in North America is 120 volts AC. 120 volts is, so that is the root mean square of the voltage. So the peak voltage in America is like 170, 180 volts. Okay, in a sinusoidal AC circuit with RMS voltage V, what is the peak-to-peak voltage? So the way you do this is it's cycling between V peak and minus V peak, and it wants to know what is the peak-to-peak voltage. So if you do square root of 2 times V, it'll get you up here, but then you need to go from peak down to peak, so you got to double it. So it's 2 times your square root of 2. Okay, so you do your square root of 2 to undo the RMS, and then multiply by 2 to go from here up and from there down to get your full peak-to-peak separation. Done with that. Okay, 9. Which quantity is most relevant when determining the damage caused to the human body by electric shock? Well, the thing you most care about is current. Generally, it's a combination of current and voltage that you need to get above a certain amount of power, but it's usually current. You need the voltage to push the current through you, but the current is what does the damage. Okay. Number 10, cell membranes contain this. Suppose a potassium channel carries 2.1 picoamps. How many potassium ions pass through this in 1 millisecond? So you've got 2.1 picoamps, which is 2.1 times 10 to the minus 12 coulombs per second. Okay, and so if you multiply that by 1 millisecond, you're going to get a total number of coulombs, which is 2.1 times 10 to the minus 12 coulombs times 1 times 10 to the minus 3 seconds. Okay, figure out what that is. That's charge. And then you're going to have 1.602 times 10 to the minus 19 coulombs electrons, right? 1 electron per this many coulombs. Multiply that to get the number of charges that are passing. Okay, 11. When current flows through aluminum wire with this diameter, the drift speed of the conduction electrons is 0.00. How many electrons are flowing past in a given section? The conduction electron density is aluminum is this. So the drift velocity for a charged particle, let me screenshot this. Okay, drift velocity is V is equal to I over NAQ, okay? And so for our area, we've got pi r squared, so we got to figure out using the diameter over 2. For that, the drift velocity is V, how many electrons are flowing past a given section, and N, the density is here, Q is the fundamental charge. So you figure all that in, and then that gives you I. Solve for I here, because what we want is how many electrons are flowing. So this, again, is coulombs per second, and then you're going to convert it to electrons per second with that 1.602 times 10 to the minus 19. Okay, 12. A wire has a current density of 7.69 times 10 to the 6 amps per meter squared. Cross-sectional wire is this. What current does the wire carry? Okay. Let's see. Current density is this. Blah. Yeah, okay. So then, let's see, which one is this? If cross-sectional area of the wire is, what current does the wire carry? Okay, so yep, so your current density is this, amps per meter squared. The cross-sectional area is for that. What current does it carry? So we have 7.69 times 10 to the 6 amps per meters squared. And the cross-sectional area is 3.41 millimeters squared. So we're going to multiply this by 3.41 millimeters squared. And make sure you get your units to work out. But if you do that, you end up with amps. So if you just multiply the two together, this is like a dimensional analysis problem. You put that in. And then with this current, how much time is required for that many electrons? So then this is 7.69 times this, whatever. Whatever you get here is amps, which is coulombs per second, multiplied by some t, and it gets you 3.11 times 10 to the 20 electrons, and then you got to convert your coulombs per second to electrons per second, and then divide that into here, and you can solve for t, how many pass in a given time. Okay, so you got a particle accelerator here, 2 beams. So we've got electrons going this way, 7,130 meters per second. If we multiply that, multiply that by 1 electron every 0.0664 meters, then we get electrons per second, and then multiply by 1.602 times 10 to the minus 19 coulombs per electron. Then you multiply that together, you have coulombs per second, and then that's current. And then you've got protons going this way, you do the same thing, but electrons moving this way is the same thing as protons moving that way. So when you calculate the current from here and the current from here, you add them together, because they're the net result is more current flowing in, more electrons, more negative charges moving that way, more positive charges going this way, so they just add together. So again, a dimensional type problem there. 14, you measure current through a resistor to be this many amps. What's the potential difference across contacts with the resistor? Okay, so this is just V equals IR. Solve for that. 15, a power supply maintains a potential voltage of this across what's the current? V equals IR. 16, what is the resistance of a wire that's this diameter? The resistivity of aluminum is this. So we're going to do resistance R is equal to rho L over A. So just do that. How long is a tungsten wire if it has a diameter of this and a resistance of that? The resistivity is this. So resistance is rho L over A. You got to calculate the diameter again. It's a wire, so pi r squared. The resistance R is 2370 ohms. The resistivity rho is this. Solve for L. I think this is like 1,000 meters or something long if I remember. 6 copper wires have the listed lengths and cross-sectional areas. The resistance R can be calculated in this, blah, blah, blah. Rank the wires from the highest to lowest. So again, you're just going to put rho equals, you've got the resistance is equal to rho and then L over A. So there's 1. Resistance is rho times 3L over A3, which becomes 9L over A, and then resistor is equal to rho L over 3A, and then resistor and so on, and then you rank them based on the size. Okay, 19. 3 resistors made out of different materials, so this is simple. All resistors are this long, provide a table, blah, 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 so you just do the total resistance is rho L over A. They all have the same length, but what's changing is the radius. You've got pi r squared for 1, you've got length squared for 2, and then you've got 1/2 length squared, or 1/2 base times height for 3, multiplied by length, multiplied by the resistivity, put them all in Wolfram alpha, you're good to go. To what temperature must you raise a copper wire originally at 21.3 degrees Celsius to double its resistance? Okay, so the resistance is temperature resistance. Let me get the proper equation from this book. Is equal to your initial resistance times 1 plus alpha delta T. Okay, and to what temperature will you raise it to double the resistance? So you want the new resistance 2R from the original resistance. So cancel that out. So you need this to be 1 plus alpha delta T. You need that quantity to get you up there. So 1 is equal to alpha delta T. So 1 over alpha is equal to 21.3 degrees minus, so it'd be T final minus initial. So T final minus this, and then so you figure out what 1 over alpha is, add 21.3 degrees to it, and then you get your what temperature it is. I think it's pretty high if I remember correctly. Okay, 21, the maximum allowed power dissipation for a 27.5 ohm resistor is stated to be 10 watts. Calculate the largest current that this resistor can safely save without burning out. So P equals IV. 10 watts is equal to IV, or I squared R. So then 10 watts divided by 27.5 ohms, square root of that should be the current. 1,000-watt toaster takes 1 minute to toast a slice of bread at 8 cents a kilowatt hour. How much does toast cost? It's pretty cheap. So P equals IV. We've got 1,000 watts is equal to energy times time. This times 1 minute, or 60 seconds. So this is equal to, so energy is equal to power times time is the equation we're using here. So that's 1,000 joules per second times 60 seconds is the total number of joules. Or if you want to keep it in kilowatt hours, you have 100,000 watts times 1/60th of an hour. Now this is, and so this would be 1 kilowatt times 1/60th of an hour, and then times 0.08 dollars, or you can just leave it as 8 cents per kilowatt hour. Cancel that, and then that gives you your answer will be in cents. Basically, your unit will be cents, and it's like 0.1 cents or something. 23. What is the current needed to transmit 115 megawatts of power? Transmission line held at 25 kilovolts. So you've got P equals IV, 115 times 10 to the 6 watts divided by 25,000 volts. Find the power loss that would occur. So then you do P equals IV or V squared over R here. And then you've got 115 megawatts. P is IV, P is V squared over R, so you do 115 megawatts squared over 1.55 ohms, and then that would be the power loss, and then that divided by your original 115 megawatts gives you the power loss. And it was 10% or 20%, I can't remember. Okay, a kilogram toy is powered by 4 batteries. So you've got what we got here is 1/2 mv squared type energy here. We got a 0.718 kilogram toy. The car has an effective conversion of 36%. After 7.88 seconds, which is initially at rest, the car reaches 3.43 meters per second. What is the average current supplied to the car's motor? Okay, so it's going to have 1/2 mv squared, and that should be equal to the energy or the power times time. Okay, and so this is equal to IV times time. So you have 1/2 mv squared is our final thing. So we have 3.43 meters per second. We've got the mass. We can get the total energy after 7.88 seconds. And we've got 6-volt battery, and we're going to do it for 7.88 seconds. So if you just solve for I, then that's the average current that you would receive from the batteries. Okay, sinusoidally varying voltage is represented by this. What are the frequency F and the peak voltage V? So from this, you just remember the equation. The sine function oscillates between 1 and -1. And so now it's going to oscillate between 65.5 volts and -65.5 volts. So that's our peak voltage. And then the number in here is omega t, and omega is 2 pi times the frequency. And so you can figure out what the frequency is by taking 110 pi divided by 2 pi. Okay, delete. What is the RMS current flowing through a light bulb that uses an average power of 75 watts when it's plugged into a wall receptacle, supplying an RMS voltage of 240 volts? So this is just a simple problem, P equals IV, but you take your 240 volts divided by square root of 2 to get your RMS, to get your average RMS current or whatever. Okay, 27, its highest temperature space heater is resistance 43 ohms, was plugged into the wall. Supplies peak voltage of 162.6 volts, sinusoidally at 60 hertz. What is the average power output? Same thing. You've got, what is this? P equals I squared R, or P is equal to V squared over R. And so we've got our 162.6 volts. Calculate VRMS, and then divide by R, and you get your P. All right. Giant electric eels can deliver a shock of 500 volts up to 1 amp of current for a brief time. What is the maximum power a giant electric eel can deliver to its prey during this time? So P equals IV, so just 500 volts times 1 amp is 500 watts. Just P equals IV. And then the body of whatever is 625 ohms. So the snorkel, how much current's going to flow through it. So you go back to P equals IV. You're starting with 500 watts. But now, well, P is I squared R. And so you can solve for what's the current if they have 625 ohms there. 500 milliamps can cause a heart fibrillation. So it should be high enough. It should be like 800 milliamps. And then what is the power received? So then you can do P equals I. V or I squared R, whatever you want to do using those values. Okay, 29. A heart defibrillator passes 10.5 amps through a patient's torso for 5 milliseconds in an attempt to restore normal beating. How much charge passes through the torso? So you've got 10.5 amps 4.5 milliseconds. So amps, remember, is coulombs per second. You can multiply by 5 milliseconds, and now you get coulombs. Okay, what voltage was applied if 515 joules of energy is dissipated by the current in the patient's body? The 515 joules of energy is equal to power times time. So then power is current times voltage. So then you can solve for what the voltage is by setting that equal to the 515 joules. What is the effective resistance of the patient's torso? So then just solve for R. And find the average resulting temperature increase of the 8.25 kilograms of affected tissue. Assume the body's temperature has a specific heat of about whatever. So you don't have to look anything up for this. You just start with this equation. You get 3.5 times 10 to the 3 joules per kilogram degrees Celsius. And then if you multiply this by 1 over 15, 515 joules, joules like that, joules goes away, and then multiply by 8.25 kilograms, then you end up with degrees Celsius, and then you take, per Celsius, take 1 over that, and then you should just get degrees Celsius. So you don't have to look anything up, it's a dimensional problem. Okay, 30. Particular circuit contains this. Only 80 ohm resistors and switches, which can be open or closed. So what we want to do is make the equivalent resistance 40 ohms. So if we have 80 ohm resistors and we want half the resistance, then we know that we need to put them in parallel. And that's it. Okay? Because they'll have half the resistance. So now we want 10 ohm resistors, and we want the resistance total to be 20 ohms. Okay, so put our 2 resistors in series, because 10 plus 10 is 20. And then let's put our switch here so that this part of the circuit is open, and we force the current to go through that way. Okay, 32. Circuit consists of 2 resistors connected to power source in parallel, as shown in the figure. The resistance of R1 is less than the resistance of R2, which has a greater voltage across it. So they're in parallel, so the voltage is the same. And which resistor has the greater current flowing to it? Well, the one that has more resistance is going to have less current, because that's what more resistance means. Okay, a circuit consists of 2 resistors connected in series. So this is the difference, the last 2 problems, between series and parallel. Which resistor has greater current flowing through it? So they're going to have the same current flowing through them in series. Which resistor is going to have the greatest voltage difference across it? So the one with the bigger resistance, V equals IR. So the bigger the resistance, the bigger the voltage drop. Okay, indicate whether the light bulbs in the circuit are series or parallel. So it should be pretty easy for you. Series, parallel, series, parallel. Okay. And 35. A charge travels from the positive terminal of 6-volt battery through a light bulb, through the battery, back to the positive terminal. The total change, so it's going to be 0 volts for this total change, because you're going to go from 6 volts through everything, drop down to 0, but when you get back to the positive terminal, you go back up 6 volts, so you're at the same potential you started with, so it's 0 volts. For 2 resistors connected in series with a battery, EMF at 24 volts and negligible internal resistance, find the current through each of these. So what you do is, first thing you do, like normal, V total is equal to I total times R total. So V total is equal to I total times, then it's R total is R1 plus R2, because they're in series. From there, you calculate the total current through the circuit, and then you know that I1 has that same current all the way through the circuit, so you just plug that in there. We got a 24-volt battery. And then to figure out the voltage across R2, take that same current and multiply by R2 resistor. Okay, 37. Find the equivalent resistance of combined resistors, blah, 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 shown in the figure. Okay, so first thing you do is combine these, and so now you have... Okay, now you have one resistor here, which is R3 plus R4. And then the next thing you do is, that's going to go like that. So then the next thing you do is combine these two into a single resistor, which is going to be R1, R2 over R1 plus R2. And then this plus that. So there's your total resistance on that leg. And then let's call this R top. So then R top times R bottom, which is this resistor, divided by R top plus R bottom, plus this resistor, R6. So this is not R bottom, we'll just call it R5. R5 is your total resistance, okay? And you could actually plug all this into Wolfram alpha at once and not do any simplification. Okay, 38. In the circuit shown, all 6 resistors share the same value, blah, blah, blah. So what you're going to do when the switch is open here, you've got R squared over 2R here, R times R divided by 2R. Oh, I'm sorry. Yeah, no, R times R, yeah, R squared over 2R. So you end up with R over 2. So this is R over 2 in parallel, and this is R over 3 in parallel, and then these two added together, so you have R over 3 plus R over 2 is your total resistance. That's when this is open. When it's closed, you have R over 3 plus R over 3, so you have 2R over 3. Okay, so then you can, using that, you can calculate your percentages from that. Okay, 39, auto mechanic, you need to determine the EMF internal resistance of an old battery. Perform 2 measurements. In the first, you apply a voltmeter to battery's terminal, you read 11.7 volts. In the second, an ammeter applies to the terminal, indicates 13.7 amps. What are the battery's EMF and internal resistance? Okay, so for this one, you've got 11.7 volts, and this is, you just have a battery sitting here with 2 terminals, so it's not hooked up into a circuit. When you measure a voltmeter across that, an ideal voltmeter is going to have infinite resistance. So there should be no current flowing out of the battery, so it should measure 11.7 volts, and that should be the true EMF of the battery. Once you hook it up into a circuit and you start drawing current through it, that's when you're going to have your a slight drop due to the battery's internal resistance, and so this 11.7 volts is going to be your EMF, and so your terminal voltage is going to be the difference of that minus I times the internal resistance. And so I is 13.7 amps, and you can solve for what the resistance has to be in order to get the total internal resistance. Okay, 3940. You have a battery marked 6 volts. When you draw a current of 0.201 amps from it, the potential difference between the terminals is 5.09 volts. What is the potential difference when you draw 0.517 amps? Okay, so you got 6 volts. When you draw 0.201 amps from it, the potential difference is 5.09. So we lost 0.91 volts from the battery. And so then that I times R, 0.201 amps times R should equal that 0.91 volts. So then you can calculate what the total internal resistance is. And then when you draw 0.517 amps, that times your new internal resistance is going to be your new drop, and then 6 minus that will be your total new voltage. Okay, 4 wires meet at a junction. The current is blah, 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 blah. What is the fourth one? Okay, so we've got what is this red? Okay, we've got I1 coming in, I2 coming in, I3 leaving, and I4 doing something. What is 4? So we know that I1 plus I2 has to equal, minus I3 is equal to I4. And so you just do this plus this minus that, and whatever's left is I4. And if it's plus or minus, it tells you whether it's going in or out of the junction. Okay, because all the current has to be conserved. All right, so we got this circuit, determine the magnitude of the currents, I2, I3, I4. So these look scary, they're not scary. This plus sign and this plus sign means that the voltage is going that way, or the current's flowing that way. In this one, the current's flowing this way, and this one's the current's flowing that way. Okay, so what you do with these types of problems, 16.5 volts, E4 is 3 volts, and so we have to do a Kerkoff's law thing here. So first thing you do, you can do a loop like this, and what it says is that E3, and then so this is going to be minus E3, because if we're going around, this is against, that's the plus side, so we're going against that, so that's going to be minus 3. As we come around, we're going towards the positive side, so that means this is going to be plus E4, and then minus I3 R3 is equal to 0. And so from there, we can solve for what the current is through R3. And then we can do the same thing here, do a loop that way, and R1 I1 plus E1 minus E2 minus I1 R1, because the current here and the current here should be the same. And then plus, actually it's going to be minus E4. And when you do that, you can solve for what I2 is, and then that should be the current here. And then I3 is, we already found that from this first loop here, solve for I3. And then the last one, do the same thing, delete. For the last one, I4, which is in the middle here, what you want to do is, you've already figured out I2, you've figured out I3, and then you need to know what is I4 doing. Either it's going towards or away from the junction, and so you just say that I2 is equal to I3 plus I4, solve for I4, and whether it's plus or minus will tell you the answer. Okay. 42, 4 resistors connected to the battery, blah, blah, blah. Find the voltage across each resistor. Okay, so the way you do this is, again, you have to simplify. So this is going to be, you got a resistor here, and then you have 2 resistors in parallel. Okay, because this one and that one add together to this new one, which is 6R, and this one is 3R. And then you know that this simplifies down to, this would be 6R times 3R, 18R divided by 9R, which would be 2R. So this simplifies down to 2R, and then plus R. So the total circuit then is 3R. Okay, and then V equals IR. So you've got 4.25 volts here, and so the voltage drop across here will be a third of that, and so you end up with 4.25 divided by 3, and there's your voltage drop there. That's the voltage drop across R1 here. And then what happens is that the voltage drops again here, and then the current splits between each of these. And so then you work backwards, and when they're in parallel, you know that, so if I go back to when I had a 3R here and a 4R here, sorry, a 6R here, then I know that I had a 4.25 volts divided by 3 here, and because of the loop rule going around, I know that 4.25 volts minus whatever this is the voltage across these two. So R4 and the sum of R2 and R3 are going to have the same voltage drop, but then within each of these, they're each going to have their own voltage drop, and those two have to add up to 4.25 volts minus 4.25 over 3, and the total resistance is 6R, so if you take the voltage over 6 and then multiply by 2 to get the voltage drop across here, or multiply that by 3 to get the 4 to get the voltage drop across there, then those two added together should be your total voltage. Okay. 44, circuit to the right consists of the battery, blah, 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 and the current passing through each of the specific ports. So the points that you want to calculate are A, B, and F. Okay, so what you do here, the total resistance here, if you treat all those as one, are, since, they're all different resistors, you're going to have to do 1 over R2 plus 1 over R3 plus 1, and calculate this resistors here. And then that plus R1, and then V over that will give you the current coming in. So now you know the current coming in, I1 coming in there, and that's also the current leaving here. And so then you go back to here, and now what you want to do is combine these two, okay? R2 and R3 into 1 and R4 and R5 into 1, because then you know that the current's going to split here, but the voltage drop is the same. So we started with 20.5 volts. You want to figure out the voltage drop here. It's like 16 volts or something. 20 minus 16 tells you each of these resistors has the same 4 volts across it. Once you have that, then you can calculate the current going this way and the current going that way using the 4 volts and the resistance of the combined units here. So that's how you can get the current at point B. And then down here, you split this back out, and you know that the current as it goes from point B is going to split here and split there. Again, you get the same voltage drop. You can find the current I3 and the current I2 here, and then I2, F, I3 adds up to your initial current, and then you can calculate the total current there at those points. Okay, 45, you get 3 ideal batteries. Calculate the current IP at this point here, and we've got the voltages and the resistance at each of these points. So again, it's another Kerkoff loop rule problem. So you start with this loop, and you say that E1 minus E2 minus I2R2 minus I1R1 equals 0. Okay, that's one loop. You got another loop here. I3R3 minus I3R3, and then minus E3, and then minus R2I2, and then plus E2 has to equal 0. Now the thing is, because R3 and R2 are in parallel, that means they have the same voltage across them. So I3R3 is, we can call it V, and then R2I2, we can also call it V. So we can do V minus E3 minus V, and then, minus V minus E3 minus V plus E2 equals 0. So then you can solve for the voltage across these, and then you can solve for the current in each of these, and then you can solve for the current because now we know what I1 is here. Once you get I2, plug it into here, solve for I1, and you can get that current. Okay, but the key here is to recognize that these have the same voltage drop across them, and you can calculate what that is using this. Okay, delete screenshot. 46, you construct a component here. So this is just testing when you're trying to measure voltage. You want it in parallel. When you want to measure current, you put it in series, and then you can connect it here. So your current meter always is in series, your voltmeter is always in parallel with the component. 47, you have this, charged with that. What is the time constant? So the time constant is just RC. So you've got a 53 millifarad capacitor times this resistor. Multiply the two together, you get your time constant. After what multiple of time constant does the potential reach 1.07 volts? So the equation here is V at some time is equal to V0 times 1 minus the e to the minus t over tau, or tau is RC. Oh, sorry, we've already charged it. We've got to, yeah, so we're discharging. Okay, so for discharge, V equals V0 e to the minus t over tau. So it's a little bit simpler. So we want our final to be 1.07 volts, and we're starting with 11.1 volts. And then if we take the log of that, we get negative t over tau equals negative t over tau. And we want to know after what multiple of the time constant does the potential difference reach 1.07 volts. So if we solve for this, and then that this number over here, if we multiply it by tau, then that's the answer. So this is the answer, and then that times this is the number of taus that we need to get to that time constant. And remember, this exponential, we're talking about charging and discharging a capacitor. So we need the two, okay. Delete 48. We've got a heart defibrillator, RC constant. Defibrillator has 7 microfarads of capacitance. What is the resistance of the path through the patient? So RC is 19 milliseconds. We've got C, just RC is equal to 19, solve for R. If the initial voltage is 12 kilovolts, how long does it take to decline to 219 volts? So we're discharging again. 219 is our final, divided by 12,000 volts is equal to e to the minus tau t over RC. Then we want to know how long does it take. So again, take the log of 219 over 12k equal minus t over RC, and then multiply by RC, and then that is the amount of time that it's going to take to do that. And then 49, you got this capacitor, blah, 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 find the resistance of the resistor. It's discharged, so we're going to do V equals V0 e to the minus t over tau, or RC. And so let's leave it as RC, because that's what we're going to solve for. So you've got V over V0, log of that is equal to minus t over RC. So then we're going to multiply by R. R is equal to minus t over C times the log of V over V0. Okay, solve for that gets you the resistance. 50. Initially charge a capacitor through the thing by the whatever. Find the time constant tau of the circuit. Okay, so you've got a capacitor and a resistor. Tau is just RC, so there you go. What is the charge Q? So Q is equal to CV. So what we need to do is find V after 1.07 tau. So we're going to say V is equal to V0, and we are charging it. So it's 1 minus e to the minus 1.07 tau over tau. So that cancels that out. And then this gives you the voltage at this time. So you solve for that and you get V, and then go back to your C here. C times V gives you the charge there. And what is the charge after a really long time has passed? It should be C times the full voltage. Okay, and then 51, almost there. 51, a pacemaker fires exactly 67 times a minute. Each time it fires, 25 nanofarad capacitors charged by a battery in series with a resistor. What is the value of the resistance? So V equals V0 times 1 minus e to the minus tau over RC. So we want R here. We're changing it to 0.682 of its full voltage. So V over V0 is equal to 0.682 is equal to 1 minus e to the minus t over RC. And it's firing 67 times a minute. So the time period is 1 minute divided by 67, because we're firing 67 times per minute, so 1 over that would be the length, and then times 60 seconds per minute, and then that will give you the number of seconds for every fire. Pew, 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 how much time is elapsing. Then you plug that in here, and so we'll have 0.682 minus 1 log of that is equal to T over RC. So we'll do the same thing. We want R. R is going to be T, which is this T over there, divided by log of this stuff times your capacitance. Okay, boom. All right, that's the assignment. Bye.